Hi everyone, my name is Mahdi and I'm a PhD student at the Australian Institute for Machine Learning, the University of Adelaide. I'm going to present the work that we have done in collaboration with Chi Wu, Asana Bosnajad, and Job Shi on visual navigation. Most of the current state-of-the-art visual navigation methods use a variant of actor-critic reinforcement learning to train their navigation agents. The policies learned by those methods cannot perform global reasoning due to the limited field of view observation, and therefore at best learn to perform some sort of random search. When these agents cannot find the target object early, they give up very soon and stop searching. In this work, we enable the agents with a better global reasoning. For example, if the agent is looking for a pot at the state T, it should know that finding the stove is a good indication that the pot might be nearby on the right-hand side. So should not give up and rather rotate right. Our solution is to incorporate the relationship between object locations or object collocation information into our navigation framework by building a neural graph. This neural graph will then be able to provide the agent with a representation that is based on reasoning on the observed objects and gives a more global understanding of the surrounding environment. In order to efficiently incorporate the graph representation into our navigation framework, we propose a novel method to improve the state value estimation in actor-critic reinforcement learning. The role of critic in these algorithms is to help with the so-called credit assignment problem. In visual navigation, it means observing what objects lead to the success or failure of a trajectory, and therefore is very crucial. Our object collocation graph consists of 4 layers, one for each room type in the simulation environment. Each layer consists of the objects observable in each room type and is extracted from the simulation environment. This helps learning different representations for the same objects if they appear in different rooms. The node features are a concatenation of the object name embedding and the observed visual representation at each time step. The edges are initialized using prior knowledge extracted from visual genome dataset. We use a self-adaptive backbone model that is a combination of a feature extractor, a pre-trained feature extractor, and an LSTM state encoder that produces the probability distribution over the actions at each time step. We then introduce our graph-based value estimation module into this framework by performing graph transformation operations that learn new edge weights between the nodes in the graph. The structure of the graph was just introduced. We next use a few graph convolution operations to extract the final graph representation at each time step. This representation is then used in conjunction with the state representation encoded by the LSTM to estimate the state value. Therefore, the value estimation is performed by utilizing both the local information and the more global representation of the observed objects and their relationships. By estimating the state value using the object collocation information, our agent is able to learn a more optimal policy since it can more accurately estimate the state value. In this graph, we can see that our proposed GVE or graph-based value estimation module reduces the error in estimating the state value compared to the baseline method. This graph has been generated using 1,000 samples from the unseen test environment. So it also shows that our GVE module learns representations that are generalizable to unseen environments. We evaluate the performance of our method using the conventional metrics in visual navigation, such as success rate and SPL. We achieve new state-of-the-art results by improving the success rate by around 3% and SPL more than 1%. We also compare different variants of our method to show how our proposed GVE module helps with more efficient graph integration into the framework. For example, we can see that using the same graph as part of the state space increases the complexity of the state space, which degrades the performance. Finally, when comparing the trajectories of our method to those of the baseline, we observe that our agent more accurately estimates the state value higher, hence being named optimistic. Being optimistic helps our agent to avoid early stopping when the object is considered within reach from a human eye perspective. Thank you very much for watching this. Please feel free to check the full paper or attend our Q&A session for more discussion.